uniqueness proofs today, and maybe in the next lecture as well. The next thing I want to talk about, which will eventually lead us back around to these ideas, is the mean value property. Okay. So the mean value property, it applies to any harmonic function. In other words, any function that satisfies Laplace's equation. And what it says is that U is harmonic, and it's C2 on some domain omega, if and only if for any ball B X with some radius R, okay? And let me just define this ball down here. I think I sort of block this out with my face, so let me write it down here. Okay, BXR is equal to any value of Y that lives in Rn such that X minus Y, the magnitude of that, is bounded by R. So it's open, and it needs to live inside of omega. Okay. So if that's true, so U is harmonic if and only if for any ball like that, that we can write the following equation, that the average essentially over the boundary of that ball is equal to the value of U at the center of the ball. Also, that the average over the volume of the ball is equal to the value at the center of the ball. Okay. So just in words, the average on the surface of the ball and the interior, okay, equals U of X itself, right? All right. And before I write down a proof, I just want to write down some intuition, which is definitely not a proof, and definitely not quite the same problem, right? But of course, it's related, okay? So if you've come across this in numerical PDEs, right? You can write down the finite difference equation for the Laplacian in 2D, right? And so, I mean, if you haven't seen this before, essentially the idea is that, you know, you can approximate derivatives by some, you know, difference of the value of that function at different grid points, right? Divided by the spatial step that you're taking. Okay, so the idea is that let's think for a bit, right, about how to write the Laplacian, right? So if I have some grid here, and I want to know the value of the Laplacian at some point xi, yi here, okay? And this is x, and this is y here, okay? Uij is equal to U evaluated at xi, yj. So we're only worried about values of U at a point in terms of in finite differences, right? So we're looking at a 2D case. In that case, the exact continuous Laplacian would be uxx plus uyy. But that written in terms of finite differences, right, would be ui plus 1 j minus 2 uij plus ui minus 1 j, all divided by h squared, okay, where h essentially is the distance between grid points. We'll assume it's a regular grid. So that's uxx, right? And then plus uij plus 1 minus 2 uij plus ui j minus 1 all divided by h squared. Okay, so this is our approximation to uyy. Okay, so in this case, right, if we have that 0 is approximately equal to this, we can take this equation and rewrite it as, or sorry, I won't do that. Laplacian of u equals 0 can be rewritten as uij is equal to a fourth. Okay, let me make these wiggly because it's still approximate, right? So I move the uij's over to the other side, right? And the h squared is a common factor that drops out, right? ui plus 1 j plus ui minus 1 j plus ui j plus 1 plus ui j minus 1. Okay, so what is this but simply the mean of the 4 nearest neighbors, right? So essentially the discrete mean value, okay? So obviously this is not a ball, right? But this gives you some idea of where this comes from. This act of saying that u is a harmonic function puts a particular restriction on the kind of function that you can have. And it seems like, at least if we approximate it in terms of finite differences, then this means that the surrounding points of u, you can average them, and essentially that determines the value of u right there. So it should follow directly from this operator. Now, this is in the discrete case. It's obviously only at 4 points, right? It's not on a ball. So we need to do this in more serious detail, okay? Probably using some ideas from vector calculus in order to do a more thorough proof, okay? So how do we do that? Well, in order to prove the mean value property, okay, we're going to start with our ball, right? And it needs to live inside of our domain, right? So let's just draw a picture of that, okay? So our domain could be any old shape. It's closed here. This is omega here. This is our domain here, okay? And everywhere inside of here, Laplacian of u equals 0. And somewhere in here, we're taking our example ball, which has x as its center and some radius r. So this is bxr here, okay? So what do we know immediately, okay? Well, let's just prove this direction, right? If the Laplacian of u equals 0, right? So now we're going the arrow to the right in the if and only if statement. We know that, well, if we just integrate over the ball, right, over the surface of the ball, the Laplacian of u, right, that should equal 0 because we're integrating 0 and we should just get back 0, right? Now we can apply Green's first identity, okay? And if we just say this is Laplacian of u times 1, if I apply Green's first identity to that, then what I get is that this is just equal to the integral over the surface of the ball du dn ds here, okay? That's the only thing that survives in Green's first identity because the gradient of 1 is just going to be 0, okay? I can write what this normal derivative is, right? Because I'm on a ball. And that's going to be the gradient of u or y dotted with my normal y minus x divided by r dsy here, okay? So this thing here, right, is my normal, okay? And so now I have this, and I'm gonna take that and manipulate it and try and prove something with it, essentially as I change R, right? But you can see already, right? I have some condition both on the Laplacian of u and the gradient of u. I'd like to go all the way to some condition on the integral of u itself, though. So can I go one step further? Okay, let's see how and do that. Okay, so the next step we take in this proof then is to set this function phi of r, okay, to be this general function of the integral over the surface of the ball, right? For any r we like, okay? So first of all, note that if u is C2, right, which it is, then what can we say? Well, the limit as r goes to 0 from above phi of r, right? If I'm averaging over a shell and I shrink that shell down to nothing, I'll just get the value at the point, okay? So that's interesting, right? So I know that this function, right, which actually appears in my theorem, at least in the limit as r goes to 0, I recover u of x. So the next step is to prove that phi of r is constant. How do we prove that phi of r is constant? We just prove that its derivative is 0. How do we prove that its derivative is 0? We use the formula that we wrote down before, okay? So that gives us our first piece of the theorem, okay? So I'm gonna show how that happens now, okay? So because I know that this is true, right? As long as I can change r and it doesn't change that, so phi of r is constant, I can get the first piece of my theorem, okay? So we just need to show that phi of r is a constant now, okay? Constant in r, right? So I'm going to compute, as I said, phi prime of r. And this is the r derivative of, and I'm going to write out this integral here, right, according to a change of variables, right? So let me, I think I'm gonna do that in pieces. Okay, so db x r u, sorry. Yeah, so if I just differentiate, db 0, 1, okay, of u x plus r z ds(z), okay, this is equal to this original integral, okay, following a change of variables given by y is equal to x plus r z, okay? Secondly, if I go ahead and take that derivative, right, then I get the gradient of u just by the chain rule, x plus rz dotted with z, because that's the argument inside of u. integrated over the surface parameterized by z, okay? But then I can define, right, what z is, and change back coordinates, and I get the gradient of u dotted with y minus x over r dsy. So change coordinates back, okay? And if I go to the previous slide here, right? Sorry, I'll get right back to it. We know that this thing is equal to 0, okay? So this is equal to 0. Therefore, phi prime is equal to 0. Therefore, phi of r is equal to a constant, which means that it's equal to the limit as s goes to 0 from above of phi of s, which we know is u of x, okay? So that's the first part of our proof, essentially showing that Laplacian of u equaling 0 implies that the average, okay, over the surface of the ball of u of y d sy is equal to u of x, okay? That's the surface. Now, what about the average over the ball b of xr, okay? Well, in that case, if we take the integral for now, I won't do the average. I'll just do purely the integral over the volume of u of y dy. I can write this out in terms of an integral from 0 to r and an integral over shells of balls with center x and radius rho, u y. This is now a surface integral, but now I'm going to integrate over all these shells, okay? So those shells are going to fill out a volume, okay? Well, I already proved something in this case, right? Which is that the average of this thing should be equal to u of x, right? So I can use my previous result, but we need these additional terms, right, that represent the dividing out by the volume. And those are going to be n alpha n, right, the surface area of these balls, rho to the n minus 1 d rho, okay? And so if I integrate up, I get alpha of n r to the n u of x, okay? And so what is this? Essentially, well, this just tells me that the integral over my volume is equal to the volume of the ball multiplied by the value at the center point of the ball. So immediately this implies that u of x indeed is equal to this average, okay? So that's the second part of the rightward arrow of this proof, okay? So we proved it for integrating over the shell of the ball. We used that result to prove it for integrating over the volume. But remember, the mean value property says that we can go back the other direction too. We should be able to say, if I have a mean value property, then I am a harmonic function on that ball, okay?